Welcome to Study Loop.
This is the answer to Chapter 21, problem number 82 from the Smith Organic Chemistry textbook. This is a great problem. I like this problem a lot. So we're told that a solution of acetone in ethanol in the presence of a little bit of acid was allowed to stand for several days, and a new compound of molecular formula C7H16O2 was formed. By IR, we only have one peak around 3000 wave number, and they give us an NMR spectrum. And we're asked, what is the structure of the product? And so I like this problem very much, as I said, because this is sort of like practical application of lots of different things, and is much more similar to like a real world chemistry application than many typical textbook problems. So we're going to take this a piece at a time and just work with each piece of information that we're given and solve the problem. So first of all, we're told that we have acetone in ethanol with a little bit of acid. And we need to know the product. We're also told that the product is of the formula C7H16O2. Okay, and so anytime that we're given a formula and asked to come up with a structure, I think that the best way to start is to calculate the hydrogen deficiency index. So remember, this is going to tell us how many how many double bonds or rings we have in this molecule. And so it's going to be 2 times the number of carbons plus 2 minus the number of hydrogens. So in this case, 2 times 7 plus 2 minus 16, all of that over 2. And when we do the math, 14 plus 2 is 16, minus 16 is 0. Obviously, it doesn't matter if we divide that by 2 or not. So we have an HDI of 0. So we have a molecule here that has no double bonds and no rings. Okay, and so from there, we can look at the other pieces of information that we've been given. The IR is kind of useless. So IR, we have the only peak we have is at 3000 wave numbers. That is going to just correspond to CH bonds, but we already knew that, right? From the HDI, we knew that there wouldn't be any double bonds. And so 3000, pretty much any organic molecule that there is going to show something at 3000 for the carbon hydrogen single bond. So in order to solve this, we need to look at our NMR data. So the NMR is pictured in the problem. I'm not going to redraw it. And we'll just take it a piece at a time. So moving from right to left, we have so let's number them. So I'll call the first one A, and A is going to be a triplet at 1.2 ppms. Triplet 1.2, and it's going to integrate to 6. Okay. Our second signal is going to be a singlet at 1.4 ppm, which integrates also to 6. And then our third and final signal is going to be a quartet at 3.5 roughly ppm. And that signal is going to integrate to 4 protons. Okay. And so we have these pieces of information. We also know that our molecule has to be either acetones which have added to one another or acetones to which ethanols have added. And So even with this NMR information that we have, it's probably worthwhile to think about what types of reactions could go on, um, and then to think about what those products might look like, and what and then see whether the information that we have matches those possible products. And so, what we can think about is we can imagine the ethanol doing a nucleophilic attack on the carbonyl carbon. The carbonyl would probably have been protonated first by this trace acid that we're told is in here. And so if we think about that happening and then think about what it would look like if that happened twice, then what we would get would be a molecule that looks like this. Oops. Right. So we would get the double ethoxide version of this molecule. With our methyl groups. So we would also still have our methyl groups from the starting acetone. And so that's definitely potentially our product, right? So we've just had two ethoxides add, and we have two remaining methyl groups. And so if we look at the signals from our proton NMR that I've labeled A, B, and C, we can think about, so what would these signals look like? And so right off the bat, we have a quartet at 3.5 that integrates to 4. So integration to 4 would be two CH2 groups. So these two CH2 groups. The chemical shift of 3.5 means that they're next to an atom that is highly electronegative. Oxygen is highly electronegative. A quartet means that these protons have 3 neighboring protons, and indeed, these protons do. So, straight off the bat, that piece of information seems to fit. So, if we look at the next piece up, a singlet at 1.4 integrating to 6 protons. So, there are two sets of 6 protons that could account for this signal. However, a singlet means that there are no neighboring protons. And so these two methyl groups together add to 6. A chemical shift of 1.4 seems right for a methyl group. And a singlet means that they would have no neighbors, and indeed these do not. So lastly, we just need to see if our last piece of spectral information fits. So another integration of 6, and indeed these two methyl groups would add to 6. A chemical shift of 1.2 makes sense, certainly for methyl groups. And a splitting pattern of a triplet would indicate that they have 2 neighbors. And indeed, those protons do have 2 neighboring protons on the next carbon. And so all of this spectral information fits with this product that we would have predicted anyway, just by thinking about what could possibly happen. And if we were to go back and consider our HDI of 0, this molecule fulfills an HDI of 0. Yeah, and we have again by IR. The IR doesn't really tell us anything. We have CH bonds, of course. Yeah, so I would say that this product certainly fulfills all of the pieces of information that we were given for this problem. And indeed, that is the correct answer. And that's the answer to chapter 21, problem 82.